Welcome to batteries. We've already talked about redox reactions, and batteries involve just another redox reaction. So a battery is a portable, self-contained electrochemical power source consisting of one or more voltaic cells. So remember, the voltaic cells just operate on redox reactions. So a battery is just one or more redox reactions occurring in order to give us energy that we can then use to power some device. So a lead-acid battery, like a 12-volt car battery in most automobiles, consists of 6 cathode-anode pairs, each producing 2 volts. And the cathode is a lead oxide on a metal grid in sulfuric acid. And we have the lead oxide solid plus HSO4 minus plus 3 hydrogen ions plus 2 electrons react to yield lead sulfate solid and 2 water molecules. And then the anode is lead, so we have lead solid plus the HSO4 minus react to yield lead sulfate plus hydrogen ion and 2 electrons. And then our overall electrochemical reaction is lead oxide plus 2 HSO4 minus plus 2 hydrogen ions plus lead solid react to give us 2 lead sulfate solid plus 2 water molecules. And then the cell potential for our reaction here is standard cell potential is equal to standard reduction potential of the cathode minus standard reduction potential of the anode, which is plus 1.685 volts minus negative 0.356 volts, which is plus 2.041 volts. And then wood or glass fiber spacers are used to prevent our electrodes from touching each other. And one advantage of these cells is that they can be recharged, so we can run the reaction in reverse. So we use some external power source, some external source of energy is used to reverse the process. So we reverse the voltage and drive our products, or our products, back to the reactants. We drive the lead sulfate back to the lead oxide and lead metal, solid lead. And we have a number of other common types of batteries. We've got an alkaline battery, nickel cadmium, nickel metal hydride, and what's becoming more and more common, especially in the proliferation of cell phones, is lithium-ion batteries. On the other hand, we've got fuel cells, and direct production of electricity from fuel cells occurs, direct production of electricity from fuels occurs in a fuel cell. So one example of this is a hydrogen fuel cell. So at the cathode, we've got 2 water molecules plus oxygen react to give us plus 4 electrons react to give us 4 hydroxide ions. And at the anode, we have 2 hydrogen gas molecules plus 4 hydroxide ions react to give us 4 water molecules and our 4 electrons back. This type of cell is known as a PEM fuel cell, or a proton exchange membrane fuel cell. And the anode and cathode are separated by a polymer membrane. That's the proton exchange membrane. It's permeable to protons but not electrons, which means that it's acting as a salt bridge. So we have the H plus ions, the hydrogen ions, are allowed to move back and forth. We have other types of fuel cells like direct methanol fuel cells, and these are similar to our proton exchange membrane cells, but use methanol as a reactant instead of the hydrogen gas. So both the batteries and fuel cells can be used to power devices. The advantage of the battery is that you don't need to have any outside oxygen around, but the problem with the battery is Once you've used up your reactant, that's it. The battery is worthless unless you can recharge it, but you still have to recharge it with some external power source. With a fuel cell, on the other hand, you can continuously supply fuel in and get ion energy out. And so fuel cells are how a lot of our spacecraft power themselves. They have some batteries on board, but they also have fuel cells. Now, with a spacecraft, you have to carry the oxygen as well as the hydrogen. But this was, say, how the spacecraft, the Apollo missions, got to the moon and back. They powered their spacecraft using fuel cells. So that was batteries.